Water treatment plants are vital for ensuring the safe and efficient supply of water in industries. From manufacturing to power generation, industries depend on clean and reliable water for various processes. Industrial water treatment focuses on removing impurities, contaminants, and solids to make water suitable for industrial use or to treat wastewater before discharging it into the environment. This article will provide a technical explanation of how industrial water treatment plants work, detailing each step in the treatment process. We will also cover important parameters monitored during each stage, ensuring optimal performance and compliance with environmental regulations. The first step in the water treatment process is raw water intake. Water is usually sourced from rivers, lakes, or groundwater and is pumped into the treatment facility. Before entering the treatment units, the water passes through screens to remove large debris such as sticks, leaves, or any other physical contaminants. Key parameters to monitor here include flow rate, which is measured in cubic meters per hour, suspended solids, and turbidity. Coagulation involves adding chemicals, like aluminum sulfate or ferric chloride, to the water, causing fine particles to clump together into larger particles. This is followed by flocculation, where slow mixing encourages these particles to form larger clumps or flocks. Important parameters to keep an eye on during this stage are pH levels, chemical dosage measured in milligrams per liter, mixing speed in RPM, and settling velocity. The water then enters sedimentation tanks, also known as clarifiers. In this stage, the heavier flock particles settle to the bottom of the tank, forming a layer of sludge while the clarified water moves to the next stage. Key parameters to monitor include settling time, measured in hours, sludge volume, overflow rate in cubic meters per square meter per day, and the turbidity of the clarified water. Filtration. The process of filtration is used to remove remaining suspended particles, turbidity, and microbes. The clarified water is passed through filters made of materials such as sand, gravel, and activated carbon. These layers trap any remaining contaminants. Key parameters include filter bed depth, filtration rate, which is measured in cubic meters per hour, particle removal efficiency, and filter backwash frequency. Disinfection, which can involve chlorination, UV, or ozone. After filtration, the water is disinfected to kill any remaining pathogens and microorganisms. This is typically done by adding chlorine or through alternative methods like ultraviolet light or ozone. Key parameters to monitor are chlorine dosage, measured in milligrams per liter, contact time, also known as the CT value, residual chlorine concentration, UV intensity if UV disinfection is used, and ozone concentration if ozonation is utilized. pH adjustment. The pH of the treated water is adjusted to ensure it is within the desired range, especially for specific industrial processes. Acids or bases, such as sodium hydroxide or sulfuric acid, are added to achieve the required pH balance. Key parameters to watch include the pH value, which is typically between 6.5 and 8.5, and the acid or base dosage, measured in milligrams per liter. Water softening or deionization, if required. In industries where water hardness affects equipment performance, water softening, which is an ion exchange process, or deionization may be necessary to remove calcium, magnesium, and other ions that cause scaling. Key parameters include total hardness, which is measured in milligrams per liter or grains per gallon, ion exchange capacity, measured in milliequivalents per liter, and the regeneration cycle frequency. Final quality monitoring and storage. Once the water treatment process is complete, the treated water is stored in large reservoirs or tanks before it is distributed for industrial use. Continuous monitoring is conducted to ensure the water meets the required quality standards. Key parameters include conductivity, total dissolved solids, microbial contamination if any, temperature, and the flow rate to the distribution system. Sludge management. The sludge generated during the sedimentation and filtration processes must be handled properly. Typically, the sludge is dewatered using methods like centrifugation or belt press. After dewatering, it is either disposed of or processed for use in other applications, such as fertilizers or in construction materials. Key parameters to consider include sludge volume and moisture content, dewatering efficiency, and sludge disposal costs. Wastewater treatment, if applicable. In many industries, the water used in processes must be treated before being discharged back into the environment. Wastewater treatment involves similar stages like coagulation, sedimentation, filtration, and disinfection. However, it may also include advanced biological or chemical treatments. Key parameters to monitor are biological oxygen demand, chemical oxygen demand, total suspended solids, and nutrient levels such as nitrogen and phosphorus. Flowchart of industrial water treatment process. Raw water intake, screening, coagulation, flocculation, sedimentation, filtration, disinfection, pH adjustment, water softening or deionization, final quality monitoring, storage, sludge management, and wastewater treatment, if needed. Conclusion. Water treatment plants play a crucial role in ensuring that industries have access to clean and safe water, while also treating wastewater to protect the environment. Each step in the treatment process is carefully monitored, and key parameters must be optimized to ensure efficiency. Understanding the technical aspects of water treatment allows industries to improve their operational effectiveness and meet environmental regulations. By managing water resources responsibly, industries can reduce their environmental footprint and contribute to sustainable water management.